Alright, this is 6-1, normal distribution. Now, we've already looked at the normal distribution before. It's this wonderfully symmetric curve. Alright? Just like we had with the last chapter where you had a discrete random variable, now we have a continuous random variable, which means that for any probability you have a value. It could be a half, it could be a third, it could be 1.5, right? So any of those are valid. In fact, over here is the formula for it, and I encourage you to look at the book for it. Y equals e to the negative x minus mu squared divided by 2 sigma squared, all divided by, the other one was part of the exponent, sigma times square root of 2 pi. We will never, ever use this formula, but it's good to know where it comes from. Now, things we need to get out of this are, and I have a list of things here, when we're talking about probabilities, we're also going to be referring to the area under the curve. Okay? So remember when we were doing the other distributions and we had these wonderful boxes and it was a graph of the relative frequencies, which was the percentages? That's the same thing we're doing now, although it's smooth, it's a continuous graph as opposed to nice, neat blocks. And when you count the area underneath the curve, like I shaded right here in the middle, that's going to be a probability. The area and the probability are the same. This is where calculus actually influences statistics and back and forth. We don't need to get into the nitty-gritty there, but we can do statistics at this level because of calculus. Now, when we talk about area under the curve, it's important to know that if you add up all of the probabilities, what do you get? So if you sum all of the p of x's, it must equal 1. Well, it's the same thing for the normal curve. Now, the normal curve, I will always draw in the same manner, but what you need to think about it is that you can change the parameters. You can change the sigma. The standard deviation changes, and you're going to change the spread of the data. And that's what this graph is showing right here. I have a standard black line in the middle of all this data, which looks normal, nice and bell-shaped, everything's regular. But if I have a smaller sigma, I would squeeze the data up. Well, what happens when you squish a balloon from the sides? It's going to pop out the tops. And that's what this green dotted line is representing. It's squishing the data. It still has to add up to 1, so I can't just make it tinier. It's going to get tiny one direction, but then expand in the other. Similarly, if I just squished it down, I have this red line where I have a big fat graph. And that's when my sigma is really, really big. Alright, so this is just getting a visual representation of what's going on. Some of the vocabulary that goes along with this is symmetric, left skew or negative skew, right skew or positive skew. Now, we call it left skew because the mean has been pulled to the left of the median. It's called negative skewed, which is the same thing, because the mean is pulled towards the negative side on the x-axis. See how it all works together? Similarly, right skewed or positive skewed literally translates or gets its name because the mean, the average of the data, has been pulled to the right of the median. To the right is also the positive direction on the x-axis. If it is a normal curve, the mean, the median, and the mode, not that we really talk much about that, all are going to be directly in the center. Alright, now I'm going to have another video talking about the idealized, the normalized graph in a second. But this is just some of the basic vocabulary I want to get through. The main thing I want to emphasize in this video, though, was the squishing of the graph. When you squish the graph, it has to pop out in another direction. Because remember, the area, the probability, must sum to 1, 100%.